Welcome back, everyone, to Chem 102. My name is Professor El Hawari, and today we will be going over experiment number 7, which is called endothermic and exothermic chemical reactions. So, the first task is you're going to make a copy of the lab report template. You can either download the template and edit it, or you can make a copy on Google Docs and also edit it as we're going, and you're going to see the document in our course documents folder. So again, at the very top, make sure to put your name and the date that you completed lab number 7. The objective for this lab, again, we need to write at least one sentence that clearly describes the goal, what we hope to accomplish, and the method used, how we plan to do this to complete the experiment. So, our objective for this lab is to observe and distinguish between exothermic and endothermic chemical reactions by measuring the temperature changes that occur during specific chemical processes. Again, our objective is to observe and distinguish between exothermic and endothermic chemical reactions by measuring the temperature changes that occur during specific chemical processes. What you need to do is just pause the video, write down your objective, and let's move on to the next section. So, as always, before we start the experiment, we are going to list the equipment that we are going to be needing for this experiment as well as their function. So we're gonna start off with beaker. As you notice, beaker has been with us since the beginning. So the beaker is a common lab container used to hold, mix, and heat liquids during experiments. Pause the video and fill your equipment table. Next, we're going to be using the beaker tongs. These safely handle hot beakers and move them on and off the heat source. We're also going to be using test tubes, so they contain a small quantity of reactants for observation of reactions. Again, we're going to be observing changes in temperature, and we will be using the test tube. We'll also be using a thermometer, and that is going to measure temperature changes during the reaction to identify heat absorption or release to see if the reaction is endothermic or if the reaction is exothermic. We'll also be using the stirring rod. This is going to serve as a mixing agent. It will mix the reactants evenly to ensure consistent reaction. Next, the disposable pipette. So this is going to add a precise amount of liquid to our reaction to get it to start. We'll be using a balance scale. This is going to measure the mass of the reactants accurately before the experiment begins. And we will be using the safety goggles, which is going to protect the eyes from splashes or reactions. All right, let's do a quick review. Now, you'll be using all of the review that we're talking about to write the final paragraph. So, we're going to talk about chemical properties. They describe how particles of substance interact with each other to result in change in composition. So, that's a chemical change. Now, a chemical change will also, as you see highlighted here, or bolded, I should say, is going to change the chemical formula. So a chemical change will change the chemical formula, and this will be observed by a chemical reaction. So in a chemical reaction, you have a substance that will be converted into one or more different substance, and that's the key thing. It has to be different, and this is done by the rearranging or moving or the replacing or the addition of the atom. So you can have atoms shifted together, they could be moved, they could be added, they could be rearranged, and you're going to get a new substance. And as a review, atoms are the smallest individual particles of an element. Now, the newly formed substance has completely different and physical properties from the starting substance. You can think of it as if you burn paper, you're going to get ash. Now, the ashes at the end have different physical and chemical properties than the original paper. Now, the chemical property, you're going to notice the keyword reacts. So when it says hydrogen reacts with oxygen to produce water, reacts would be a chemical change. So the equation now in words, we're going to say hydrogen reacts, we're going to put a plus sign. Oxygen is oxygen to produce, so we're going to draw an arrow, and water. As we discussed in the lecture class, anything that's written before the arrow is known as the reactants. These are the starting materials. And anything after the arrow are called the products, which are the final materials. In this case, we have two reactants, hydrogen and oxygen, and we have one product as shown, which is water. So let's talk about some examples of chemical properties. Flammability, the ability to burn or catch on fire, is a chemical property. When you see the word reacts with, combustion, forms a precipitate, oxidation, tarnishing, rusting from oxygen, and decomposition. There are many more, but these are the keywords that when you see, you know that you have a chemical reaction and you're describing chemical properties. Now, precipitation, as you can see, is shown here when you mix two colorless liquids, and in this case, you got a solid. And in this example, the color of the solid is yellow. The yellow solid is called a precipitate, and this is a precipitation chemical reaction. The thing we need to know about chemical reaction is that they are irreversible, so you cannot go back. Once you, for example, once you burn something, you cannot unburn it. Inertness means that they do not react, and is also important. It's an important chemical property, and the uh, elements on the periodic table that are inert are the noble gases because they do not interact or react with another element. Let's talk about the chemical equation. Again, we discussed this in today's or this week's lesson, chapter number 7. The chemical equation, you have reactants, which are written on the left side of the arrow. The arrow is like your equal sign. And then the right side of the arrow, you have your products. So the arrow symbolizes how the substances are changed by the chemical reaction. Another thing you see is the letters inside the parentheses. AQ means that MgNO32 is aqueous, which means it's dissolved in water. And the NaOH sodium hydroxide is also dissolved in water, so we put AQ. The sodium nitrate, NaNO3, is also aqueous, dissolved in water. However, the magnesium hydroxide on the right side here is the letter S is next to it, which means it's a solid. So this is actually what we're going to learn. This is a double replacement reaction, and it forms a precipitate. It forms a solid on the right hand side, right here that I'm circling. The numbers at the bottom, the three in front of the three below the oxygen and the two, are called the subscripts. These represent the ratio of the atoms in your compound. This is different from the number that's written in front right here. For example, the 2 in front of NaOH or the 2 in front of NaNO3. And now the MgOH2, there is no number on the left, but if there is no number, we're going to say the number is 1. So these represent your coefficients right here. So the coefficient tells you how many units of each substance are involved in the chemical reaction. For example, we have 1 MgNO32 plus 2 NaOHs, which is going to give us 2 NaNO3s and 1 MgOH2. They are called the coefficients. Now, the physical state, we went over AQ, which is aqueous, which means it's dissolved in water. It's a homogeneous mixture. S is a solid. Now, if you see L, that means it's a pure liquid. And if you see G, that means it's a gas. One thing that we have to know is that chemical equations must be balanced. They have to be balanced because the atoms are not created or destroyed in the chemical reaction. The number of elements that you see on the left side must match the number of elements that you see on the right side. As an example, if you see we have Na sodium, we have two Nas on the left side, and we also have two Nas on the right side. So the Nas are balanced. If you look at nitrogen, there is one, we got one nitrogen, but there's a two in front. So from math class, you distribute. So two times one, we got two nitrogens on the left. If you look on the right, also two times one is two. So that nitrogens are also balanced. Let's look at the hydrogens. The hydrogens, we got two hydrogens right here. Two times one is two on the left side. On the right side, we also have two times one is two. So now the Nas are balanced, the hydrogens are balanced, the nitrogens are balanced. Let's check the oxygens. Two times three, we got six oxygens plus two times one. So we have a total of eight oxygens on the left. Let's check the oxygens on the right. Two times three is six, and then plus 2 times 1, that's 8. So also the oxygens are balanced. If at all you have an equation that's not balanced or an equation that's unbalanced, you are going to change the numbers in front, the coefficients. You never change the subscripts, but you do change the coefficients. So let's put this to practice. It says how many reactants are there. So as you can see, we have one, two. So we're starting with two reactants. These are the C2H6 and O2. So we're starting with two reactants. How many products are there? Also two. We have carbon dioxide, which is one product, and we also have H2O, which is the second product. Question number 3 says, are there any liquid in the equation? Identify them. There is one liquid, which is right here, H2OL. That means it's on the product side, so this is a liquid. Number 4 says, what is the physical state of oxygen, O2 in the reaction? If you look at O2 right here, the physical state is G, which means it's a gas. Very good. And to review, C2H6 is also a gas, CO2 is also a gas, but H2O, as we said, was a liquid. 5, what is the coefficient of carbon dioxide? So carbon dioxide is CO2, which is right here. The coefficient is the number written to the left. The coefficient of CO2 would be 4. Excellent. And number 6 says how many carbon atoms are in the reactants and in the products. So we look, carbon is the first reactant. We have a coefficient of 2 and a subscript of 2. What we do is we multiply the coefficient by the subscript. So 2 times 2 is 4. So we have 4 carbons on the left. Let's look at the carbons on the right. The coefficient is 4, but we don't see any subscript. If we don't see any subscript, we assume it to be 1. So 4 times 1 is 4. So you got 4 carbons and 4 carbons, 4 on the reactant side and 4 on the product side. Now, these are the evidence that a chemical reaction has occurred. Uh, Color change is important. For example, if you cook meat, you're going to notice that the meat changes color because it's a chemical reaction. Colorless, like water, also counts. Sometimes you can get a colorless reaction and it's a chemical reaction, but there's usually a color associated with chemical reactions. If you form a gas, you're going to see bubbling or foaming. If the reaction takes place in a liquid, that's a chemical reaction. As we said, if you see a precipitate, which is an insoluble solid product that forms when you mix two liquids, it is not the same thing as freezing, and it's not a different physical change. It is a new product that settles to the bottom uh, because it's a solid. Now we have two more reactions we're going to go over today. We got the exothermic reaction and endothermic reaction. Exo, the word exo, you can remember as exiting. So it's a chemical reaction where heat is released. So the surrounding is going to feel very warm or very hot to the touch. So how are we going to monitor this? If the temperature is increasing or if it's very hot to the touch, It's an exothermic reaction. What about an endothermic reaction? These reactions absorb heat from the surrounding, so they're going to make the surrounding a lot cooler. So, what we care for exothermic and endothermic reaction is the surrounding. So, this is like the cold pack, it gets colder and colder. Many reactions take place without any visible changes. Other methods are required to confirm that a reaction has occurred. This is something important to note. Another thing we want to note is that when you mix substances in other materials or change state, you may observe an absorption or release of heat. This will be considered a physical change. A chemical reaction does not take place when you dissolve or mix. Very important. So when ice melts, or when you mix salt in water, or when you mix sugar in water, these are all physical changes because they are reversible. If you melt ice, you can freeze it and you're still going to get water. If you mix salt and water, you can boil the salt water homogeneous mixture to get the salt back. So this will be considered a physical change, which is very different from chemical change, which is what we're seeing today. All right, let's talk about the type of reactions. We have something called a single replacement reaction. This is when you're starting off with an element plus a compound on your reactant side, and then they are going to swap partners, and you're going to get a new element and a new compound. So if you look here, the element A was by itself, and the compound BC had the elements B and C. Now what happened is A came in and it kicked out element B, so it replaced it. That's a single replacement. So let's look at the bottom example. We got the element Cu. It's like A in our example, and then we have 2AgNO3. Now the Cu is going to come in and it's going to kick out the Ag. Now this is a red brown copper metal, which is right here, and it will dissolve, and silver metal is going to precipitate. So it's not just going to dissolve, it's going to kick out the silver, and it's a single replacement reaction. The second example, we have sodium metal is going to, when you add it to water, it's going to create this big explosion. It's going The sodium is actually going to kick out the hydrogen. Look here, it's kicking out the hydrogen. It will take its place and it will form the base sodium hydroxide. How do we know that this is a chemical reaction? Because when you do this in lab, you're going to see a lot of bubbles, which means the hydrogen gas is being produced. And what we could do in lab is something called the popping sound, or the testing for hydrogen by burning it. If you burn hydrogen, hydrogen is flammable, and you're going to hear a distinct popping sound, which proves that this equation happened and it's a chemical change. Let's talk about a double replacement reaction. This is when you have two compounds and both of them are switching partners. For example, A plus B gives you CD. Now the A now pairs with D and the C pairs with B. So let's see, AgNO3 plus KBr gives us AgBr plus KNO3. The Ag now is going to pair up with Br. The K is going to pair up with NO3, and now the AgNO3 and KBr were colorless liquids, but when you mix them together, you're going to get a white precipitate solid right here, the AgBr. Another example is the acid-base neutralization reaction, where the hydrogen is going to pair up with the OH, giving you water, and the Na is going to pair up with the Cl, that would give you NaCl, which is salt. So now forming liquid and solid, or forming the solid and the liquid are double replacement reaction. Some other double replacement reactions can form more than two products, and including a gas, which also counts as a double replacement reaction. The last thing is a double replacement reaction is also known as a double displacement reaction. Let's talk about today's experiment. We are going to be testing four reactions right here, as you can see, and we are going to monitor whether they are endothermic or exothermic. So reactions 1 and 4 will be performed in beakers, 2 and 3 will be performed in test tubes. When test tubes are not in use, we're gonna put them in the test tube rack. The absorption or release of heat will be observed by touching the beaker or test tube after the reactants have been mixed. When we touch it, we're going to figure out if it's getting hot or if it's getting cold. If it's getting hot, that will be exothermic. If it's getting cold, that's endothermic. We're going to write down our observations, appearance of each reactant. So you're going to find the data table in our lab. We're going to use the scupula to transfer some zinc metal to a beaker right here, the reactant. We're going to start off with zinc, and then we're going to add, using a disposable pipette, a few milliliters of copper 2 sulfate, which is our second reactant, and we are going to observe what's going to happen. Now, if you look, we're predicting this to be a single replacement reaction. The zinc is going to kick out the copper. The second reaction, we are in a separate test tube. We're going to add sodium. We're also going to be doing this with a magnesium strip. We're going to take some tweezers, add magnesium for reaction 2. In using clean disposable pipette, we're going to add some hydrochloric acid, which is very strong acid in your stomach. Now we're predicting the magnesium is going in a single replacement reaction, kick out the hydrogen, giving us hydrogen gas and magnesium chloride. Again, we're going to see if this is endothermic or exothermic. We got two reactants on the left, two products on the right. The third reaction, in a separate test tube, we're going to use scupula to add some sodium bicarbonate, NaHCO3, that will be our reactant. And then we're going to add some HCl, hydrochloric acid, to it. Now notice we are predicting that this will be a double replacement reaction. The Na is going to pair up with the Cl, giving us NaCl, and the H is going to pair up with the HCO3, giving us H2CO3. But notice H2CO3 is very unstable. Once it goes into water, it will break even more to carbon dioxide and H2O, and carbon dioxide will leave the system. And this leaving of the system is what drives this reaction to completion. And the final reaction is we're going to add a few grams of ammonium thiocyanate, this reactant, and we are going to add it to our barium hydroxide. And again, we are going to get a double replacement reaction. And this reaction is so interesting. It will generate ammonia gas, and it will generate another precipitate right here, which is the barium thiocyanate. All right, let's start the experiment and see which ones are endothermic and which ones are exothermic. So make sure you're filling out the data table and writing down the reactants, the products, the observation. Is it endo or is it exo? So let's start. We're gonna start with some zinc. Zinc would be our first reactant, and then the copper sulfate right here, which is the blue solution. We're predicting a single replacement reaction, and let's start the experiment. So here is the experiment. Adding it to our test tube number 7. Goes to the bottom, and look at the color. Note the color. Zinc has a characteristic metallic color. And then we are going to take the copper sulfate with a disposable pipette. We're going to be adding some to a beaker so that we do not contaminate the copper 2 sulfate solution that we created. And then we're just going, and it's also easy to pour. We're going to take our beaker, we're going to take the disposable pipette, take some liquid into the pipette, add it, and let's know what's going to happen. We're going to add it, and immediately you're going to notice something. Look at that. Do you see it? It's turning black. See that? Or actually the zinc, no more zinc. Well, you see some zinc floating, but zinc now is going to be replaced by copper. So now we are going, the zinc is going to take copper's place, and the copper you can see is at the, see, that's the copper that we're talking about. We got a lot of copper now. Very interesting. So we can, and let's touch it to see, is it getting hot or is it getting cold? And it's getting warm. So would we say is it exothermic or endothermic? So for reaction one, we would say it's exo with an X, exothermic, because it's releasing a lot of heat. So it's an exothermic reaction. Let's look at the second reaction. We have a piece of magnesium right here, magnesium strip. That's the reactant. Hydrochloric acid right here is the second reactant, and we are going to mix them together. Now we should see hydrogen gas and magnesium. We're not going to see the magnesium chloride because it's dissolved in water, but we can see the hydrogen gas. So in this reaction, we're going to take a piece. Again, magnesium is our reactant. So as you can see, it's a strip. It's metallic. It's a solid. And the hydrochloric acid is a very strong acid, and it's the acid found in your stomach. All of our stomach has stomach acid, and that's the reason why the food gets digested in our body. All right, we're going to make sure the lid is closed. Again, with uh, a clean pipette, disposable pipette, we are going to add. Now, watch what's going to happen as soon as we add the acid to the magnesium. All right, we are adding it. The reaction immediately starts. Vigorous reaction. And all this gas that you're seeing is hydrogen gas right here. This is hydrogen gas. Now you might, and look, this, all this is hydrogen gas. You might be thinking, now if we touch this, is this hot or is it cold? You might make a guess. Just make a guess based on the observation, and then we're gonna show you. And actually, it's kind of like you can see the telltale signs here. Is it getting hot or cold? See, the piece of magnesium fully reacted. And now everything fully react, kind of like disintegrated, and it turned into H2 and MgCl2. So this is the reaction, and we're going to touch it. We can see we can do it one more time with a bigger piece, and notice that the acid is like eating it. It's eating the metal. Now, is it getting hot or is it getting cold? It's getting extremely, extremely hot. Very hot, as you saw. It's getting extremely hot. So again, is this exothermic or endothermic reaction? Two is also exo with an X, exothermic reaction. All right. The next experiment, everyone, write down your observation. Sodium bicarbonate is NaHCO3. This is a white solid, and we're going to mix it with acid, which is a clear liquid. We got two reactants, and let's see the products. We should also be getting a gas in this experiment, and it will be carbon dioxide. So let's add our sodium bicarbonate. It's a white solid. We're going to add it to our test tube using the scopula. Yes, a clean scopula. We're going to add our sodium bicarbonate. We're going to close it. I'm going to take some 6 molar hydrochloric acid, very concentrated, and then we're going to add it and watch what happens as soon as we add the acid to the sodium bicarbonate. Okay, look at this. A vigorous reaction, just like the metal in acid. Look at that. Look at that. And the reason, oh yeah, and that didn't even have time, the sodium and didn't have a chance. It reacted immediately. See? You see? It reacted right away, because we have a very strong uh, acid, 6 molar. So is it hot or is it cold? It is actually very cold. Believe it or not, it's very cold. So this reaction is the reaction that occurs in cold packs that you buy, and this would be considered endo with the endothermic reaction. The last reaction we're going to see is the reaction of ammonium thiocyanate, the NH4SCN, with the barium hydroxide. We should be getting ammonia gas and a precipitate. Let's watch the reaction and make sure to note the color, make sure to note the state of matter of the reaction. So here we're starting off with a solid. We're going to go ahead, take our scopula. We are going to scoop some ammonium thiocyanate. Notice it's a white solid. We're going to put it in the test tube. It's a solid. State of matter is solid. Next, we're going to take some barium hydroxide, which is also a solid. It says crystalline. Crystalline means it's a solid, and still it's a white powder. So we're going to take this much. Look, it's a crystalline structure. Barium, it is barium octahydrate. Octahydrate, that means it's a hydrate. Has some water. Now we're going to mix it. Yeah. Notice when you put two solids together, do they react? Very slowly, not much. So we need to start the reaction. So what we're going to do is we're going to try to agitate it. We're going to mix it physically. Because when you got solid on solid, nothing happens. You got to agitate the solid-solid mixture. When we're agitating it, we're creating heat, and this heat is going to melt the two solids. Now, one of the solids, as you saw earlier, said it was a hydrate. Hydrate means it has some water in it. So see, this is enough water that will get the reaction to start. Liquids react faster than solids. All right, so here it is. Now, it was not like the other reactions, which was very evident, but nonetheless, you can see there is a white solid here, and it's very cold. This reaction could also serve as a cold pack. So for reaction 4, everyone, you're going to say this was an endothermic reaction. So to review, the first two reactions were exothermic because when we touched it, it was extremely hot. And the next two reactions were endothermic. They were extremely, extremely cold. Exothermic, two reactions. The next uh, reaction 3 and 4 was endothermic. Reaction 1 and 2 was exothermic. So, very important. The summary is at the end. You're going to write one or more paragraphs. You're going to summarize the results of this experiment. Make sure to write in full sentences. Make sure you're describing the results, not just, you know, the observation and an explanation. Describe any trends or patterns. Make an effort to support your statements by referring to the theory that we discussed. For example, how can you tell when a reaction is exothermic or endothermic? Support your statement from examples from the data that you collected today. So thank you for watching the video. Announcement reminders: you're expected to watch the assigned video, which you did. Second, you complete the quiz based on the experimental video. And three, make sure to submit your lab report given the template based on the experimental video. Thank you for watching and see you soon.